Hi, my name is Min Jae Chong from Keysight Technologies. I am the product manager for the Infiniium line oscilloscopes. Today I'm going to show you some signal integrity performance of the scope. Signal integrity is really important for your measurement to provide you with the highest measurement accuracy to create technology breakthrough. Signal integrity is very important for your digital validation as well as for your optical coherent modulation research as well. There are three different demos that I would like to show you today that can show you the signal integrity performance of the scope. First is the magnitude and phase response flatness of the scope. Second, we're going to show you the E-knob performance of the scope. And third, we're going to show you how you can achieve 4 channels up to 63 GHz by combining 2 scopes together and how we can synchronize the scope very tightly. So we are talking about very low inter-scope jitter between the scopes. So first, we're going to show you the magnitude and phase response of the Z series oscilloscope up to 63 GHz. We have a step generator that is generating a 5 picosecond step into the 63 GHz channel of the oscilloscope. So as you can see on the screen, we have a fast step response, which we then differentiate to generate the impulse response in the green color waveform. And then we will perform the FFT magnitude and phase measurements, as you can see on the blue and the purple waveform. This step generator is calibrated towards the NIS photodiode for traceability. And we have characterized the error of the step response as well. So when we subtract and corrected the phase and the magnitude of the scope, this is the plot that we get. And you can see how flat the magnitude and phase of the oscilloscope is. So we're talking about a magnitude of plus minus 1 dB up to 63 GHz, and also a phase error of less than plus minus 10 degree of error. In the second demo, what I want to show you is the E-knob performance of the oscilloscope. According to the IEEE, the way you measure and analyze E-knob is by injecting a pure sine wave into the input channel of the oscilloscope using a sine wave generator. And then the error that the scope measure of the sine wave is then the E-knob of the scope. So the more error that the scope measure, the less E-knob the scope is going to have. So what I have done is I have swept the frequency of the sine wave generator so that I can capture the different frequency data point of the E-knob for the oscilloscope. And then I feed all the waveforms into the script for me to generate the plots that you can see over here. So I have characterized the different data points up to 60 GHz, and you can see that the E-knob of the scope is at about 4 bits, 4 effective bits. This is probably the best you can find in the industry for bandwidth up to 63 GHz. So some of the competitors, right, that we have has about 0.5 dB lower, and that can affect the accuracy of your error vector magnitude measurements for your optical coherent modulation research. In the third and final demo, what I want to show you is the multi-scope application. So multi-scope is needed when you need a higher channel count of more than 4 channels. So in this case, we have 2 Z series oscilloscopes that we combine to achieve 4 channels at 63 GHz. And of course, the multi-scope allow you to combine up to 10 oscilloscopes, so you can really get to 20 channels of 63 GHz. When you are combining the scope, one of the important characteristics is how tightly you can couple the scope, because the jitter and the skew between the scope can affect your measurements and your EVM. So what I want to show you here is how we can effectively calibrate out the jitter and skew of the different oscilloscope. So we have done the calibration that will track the jitter and also the temperature drift of the scope. And the way we can prove it is using a sine wave generator. We split the signal coming out from the sine wave generator into the channel 1 and channel 1 of the 2 oscilloscope. So let's look into the screen of the scope software over here. You can see that right now we are tracking the jitter and also the drift correction. So the frame are tightly synchronized right now. The next thing is what we are doing is we actually injecting a sine wave, and split it into two paths. What we do is we actually intentionally skew the waveform a little bit, and then we measure the jitter of the second waveform, second channel, relatively to the first scope. And you can see over here, the standard deviation of the jitter is 146 femtoseconds. That is how accurate we can tie the scopes together to provide you with the most accurate measurements when you need more than 2 high bandwidth channels. We have shown you 3 demonstrations earlier. The first is the magnitude and phase response of the oscilloscope, and you can see how flat the magnitude and phase of the oscilloscope can be. Secondly, we show you the E0 performance of the oscilloscope. We measure 4 effective bits up to 63 gigahertz, and that is probably the best you can find in the industry. The third is the multi-scope application. So we are combining 2 scopes together and as if they're coming from the same scope. So you can observe that we can measure less than 150 femtoseconds of interscope jitter between the scope. Signal integrity is really important and it's the key focus of Keysight, because we understand that you need the performance for you to create technology breakthrough and to make the highest measurement accuracy for your product design. If you need more information or if you need a live demo of the scope, please do not hesitate to contact us. Thank you for watching the video today.